Good morning, everyone. I'm Wei Danji from Shanghai Jiao Tongyu University, and I'm happy to present our work, Adaptively Secure IBE from Lattice with a symptomatically better efficiency. This is a joint work with Zhedong Wang, Lin Lu, and Da Wugu. I will introduce our work with the following outline. First, I will recall some previous lattice IBE schemes and point out their common restriction. Then I will show our idea to remove this restriction. Next, I will propose our two novel techniques to realize our idea. And finally, I will propose our new lattice IBE framework and apply it to some previous IBE constructions and show our improvement. First, I will recall the syntax of the identity-based encryption, including 4 algorithms: setup, keygen, encryption, decryption. The IBE differs from PKE with an additional setup algorithm. It can be used to generate the mask public key and mask secret key. The mask secret key can be used to generate the key pairs for any identity. And the key pairs can be used in the encryption-decryption algorithms. And now, in the standard model, most adaptively secure lattice-based IBE follow the ABB framework. But unfortunately, there is a restriction common to all the lattice-based IBE following this work. Lattice modulus is quadratic in the trapdoor norm. In the next page, I will recall the ABB framework and explain this restriction. Let's look closely at the ABB framework. In the setup, they generate a matrix B and its trapdoor TB. The matrix B is statistically close to a uniform matrix, and they sample a uniform vector U and some uniform matrix Ci. And in the keygen, they homomorphically compute CID from the CIs and identity. And in the security proof, the CI would be replaced by an encoding of some kappa I. And after homomorphic computation, the CID is an encoding of some function FID. The keyed function F is a partitioning function, which partitions the identity space. More precisely, it has a high probability that FID1 to FIDQ are not to 0, but FID star is 0, where ID star is the challenge identity. And then they use the trapdoor TB to sample the short vector XID such that B concatenates CID equals to U, and XID follows a discrete Gaussian distribution. In security proof, to answer the key queries, they use the RID and trapdoor TG to sample the short vector XID, which results in the XID's Gaussian width, theta, is larger than the RID's norm. And the XID is the user's secret key. The encryption algorithm is very similar to the dual regev encryption, but differently, the error W in the ciphertext C1 is very large. This is because they use the LW samples and RID star to simulate the challenge ciphertext C1, which results in the error W Gaussian width is larger than the RID star's norm. Finally, the decryption algorithm is just the same as the dual regev decryption algorithm. Here we can see the error term is mainly the inner product of the error W and the secret key XID. And both the W and XID are larger than the RID's norm. So we have the error term is quadratic in the RID's norm. To ensure the correctness, the modulus Q should be larger than the size of the error term. So the modulus Q is quadratic in the RID's norm. This is a restriction, what we want to remove. And now we summarize the restriction in this figure. Both W and XID are in red. The red means it has a large Gaussian width. To remove this quadratic restriction, we propose a cross-multiplication design. More precisely, we want to get a top small and bottom large arrow W and the top large bottom small secret key XID, such that we can get the inner product becomes small times large plus large times small. Thus, we can remove the quadratic restriction. Next, I will show two novel techniques how we get such a hybrid arrow and hybrid secret key. Let's first recall how the previous IBEs get the secret key. They homomorphic compute CID from CIs and ID. In security proof, the Ri in Ci is small norm, but after the homomorphic computation, the RID becomes large norm. And they use the trapdoor RID to sample the short vector XID, which results in the XID's Gaussian width. Theta should be larger than the RID's norm. Since RID is large norm, so XID is large norm. Now our idea is to reduce a large norm RID to a small norm RID. But we don't know how to achieve this directly in such encoding form. So instead, we use a new encoding form, that is GSW encryption form. In such form, we can reduce the large norm RID to a small norm RID. More precisely, we can see the left CID is a GSW encryption of FID with a large noise RID. And we use a bootstrapping-like approach. In more detail, it's an incomplete decryption. And we can get the right RID. We can get the right CID, which is an encoding of FID with a small noise RID. Not that this is just an approximation. Exactly, the CID is BRID plus FIDG plus EID. Well, the RID is a small norm matrix, and EID is a large norm matrix. And in our security proof, we use RID, EID, and trapdoor TG to sample the short vector XID such that the XID is a hybrid form, where the top part is related to the EID and the bottom part is only related to the RID. So we have a top large and bottom small hybrid secret key XID. Please note that here we change our public key by adding an identity matrix IN to match our modified secret key. So now we get a hybrid secret key. So next I will show how we get a hybrid arrow. Let's first recall how the previous IBEs get an arrow. The CID stars equals to BRID star since the FID star is 0. And in the security proof, they use the LW samples and RID stars to simulate the challenge ciphertext C1. And the W's Gaussian width sigma is larger than RID's norm. But in our challenge ciphertext, there are some differences. The first difference is we want to get a hybrid arrow. That is a small norm W1 and a large norm W2. And the second difference is the CID star now is equals to the BRID star plus EID star. And the third difference is our user's public key should be aided by an identity matrix I. And now we want to simulate the challenge ciphertext. But we don't know how to use the previous LW samples B, VB plus Y, and the RID star, EID star to simulate our desired ciphertext. So we use a new LW samples BI, VBI plus Y, and ID star, EID star to simulate the bottom part of the ciphertext. The intuition of this simulation can be shown in this matrix multiplication. By this equation, we can get the correct matrix. Please note that now the challenge ciphertext C1 is not secure because we can get the V plus W1 directly since the identity matrix just be set in the user's public key and it will reveal some information of the secret V. So we need to add a square matrix D to mask the identity matrix and to protect the information of the secret V. So correspondingly, we use some new LWE samples and ID star, EID star to simulate our challenge ciphertext C1 and get our desired hybrid error W1, W2, where W1 is small norm but W2 is large norm. Putting everything together, we show our new IBE framework. In the setup, we need to add an additional square matrix D. And in the keygen, we use the GSW encryption form as the CI, and we get the CID equals to BID plus FIDG plus EID, where RID is small norm, but EID is large norm. And we use the RID and EID to get our hybrid secret key. And similarly, in the encryption algorithm, we set a hybrid error where the W1 is small norm, but W2 is large norm. And we simulate the challenge ciphertext C1 as we said in the last page. And in the decryption algorithm, we can get the new error term is a cross inner product. Well, on the left is the hybrid error, the right is the hybrid secret key. So now the error term is just linear in the RID's norm. By this way, we can successfully remove the quadratic restriction. And now I will apply our new IB framework and show our improvement. The modulus and the Gaussian wise of the secret key of some previous IB constructions are shown in this table. And after applying our framework, these parameters will be significantly reduced. Please note that our new IB framework is general. It is not restricted to any specific partitioning function, nor limited to integer or ring settings. But in our paper, we only apply our framework to one IBE to keep the symptotically smallest and mass public key size. You can find the full version of our paper via this link. Thank you very much for listening, and I'm happy to answer any question.
Okay, so we have 5 minutes for questions. Maybe I can start with the first one. So, does your technique apply to other advanced encryption schemes like ABE or IPE? So not restricted to IBE?
Yeah, it can be applied to ABEs or identity-based inner product functional encryption. Yeah.
Okay. So, any other questions? If not, then let's thank the speaker again. So the next talk will be adaptively secure big key identity-based encryption. And the speaker will be Jeff Champion, who is a PhD student from UT Austin. Please. Do you get the mic? No. Oh, you can use this one.
Okay. Hello. Okay, hello everyone, I'm Jeff, and today I'm going to be talking to you about adaptively secure big key identity-based encryption, which is joint work with Brent Waters and David Wu. So to start, we're going to be talking about breaking encryption. So suppose Alice is interacting with a server with some symmetric key under some symmetric encryption scheme. One thing the adversary can do is really just break the cryptographic assumption underlying this symmetric encryption scheme. This is sort of what we model for typically in the theoretical cryptography. However, reality is usually not so simple. So typically what's going to actually happen is that the adversary is going to just take the key directly and entirely dodge the cryptography. And this can be captured by the notion of a key exfiltration attack, where you can imagine the adversary hacks into the server and gradually steals the key. And at some point, the server might notice this, but it could often be the case that the entire key is stolen by the time that this happens. And in such a case, even leakage resilience or some guarantee like this is not going to be helpful. So what can we do about this? Well, one straightforward solution is this notion of big key cryptography introduced by Bellari, Kane, and Rugway. In this setting, basically the keys just become gigantic, like say 1 terabyte, and the idea is that if the adversary tries to exfiltrate the key, it's a lot more likely to get noticed before a significant fraction is taken, and thus we can hope for some sort of leakage resilience to carry through for security. Okay, but one issue with this is that maybe the efficiency gets totally blown up here because the key is gigantic. And so we require that encryption and decryption time should be independent of the key length given some random access to the key. Okay, so basically the only overhead we have to deal with is the storage of this gigantic key. However, this can still be a bit of a problem if Alice has a bunch of devices, say including a smartphone, and she wants to store the key on all of them. Well, if the smartphone only has 32 gigabytes of memory, it's not going to be able to store a 1 terabyte key. So what we'd like to do is maybe find some sort of technique that can be used to get some kind of meaningful security in such a setting. And something that's going to be helpful in doing this is this notion of identity-based encryption, or IBE. In this setting, we have basically a public key encryption scheme where ciphertexts are associated with an identity, as are the keys. And we want the property that if the identities on the key and the ciphertext match, then we can decrypt. Otherwise, even a group of adversarial users is not going to learn anything about the message. So how do we apply this to the big key setting? Well, Dotterling, Garg, Sakar, and Wang introduced this notion of big key identity-based encryption, which is the following setup. Basically, we're going to take a master secret key to be the large 1 terabyte key. And what Alice is going to do is give out short identity keys to each of her devices, where you can imagine that the identity here is like the current date, and these keys get refreshed every day. And we want the property that we can generate these short keys given local use of the master key. So in particular, these should be independent of the master key length. Okay, so that's basically the functionality here. So how does security change? Well, basically we want that adversary cannot break more identities than the ones that it individually steals and that are going to be trivially leaked by leaking part of the big master secret. The reason that they'll get trivially leaked is because, again, we make local usage of this to generate the short keys. So a bit more formally, basically the setup is the following between an adversary and a challenger. The challenger is going to generate the master secret and the public parameters or public key. the adversary is going to make identity queries and get a secret key in return. This captures the idea of stealing individual keys. And then at some point later, it's going to ask for its leakage of L bits. And then some point after that, it's going to declare a set of challenge identities, J, where the size is going to kind of depend on the amount that you've leaked, because that determines how many you've trivially stolen. And basically, the adversary must break security for all sort of identities in the challenge set. So yeah, that's basically the security game. Okay, so what did the prior work show? They showed how to construct PKE I from standard pairing-based assumptions. However, they only satisfied the notion of selective security, where that challenge set J is fixed before seeing the public parameters. And in particular, this is especially difficult here because with many challenge identities in the set, it's not clear how to generically upgrade like you can with standard IB, because they're basically the set is going to be a bit too big to guess, for example. And so what we ask in this work is, can we get adaptive security from standard cryptographic assumptions? And what we show is that indeed we can. We show a construction from indistinguishability obfuscation, or IO, along with one-way functions. And additionally, we show a construction from witness encryption along with pairings. And in this talk, we're mainly going to focus on the IO construction since it's a bit simpler, but still captures the main ideas. Okay, so now let's get into the construction. Before I get into the actual construction, I'm going to start with a template, a general framework for how we're going to approach this. So the idea is the following. The master key is going to consist of a bunch of uniform random bits. The public parameters are going to be commitments to those bits, and then additionally the master key will have the openings to those commitments. So something you might notice here is that the public parameters are actually going to be gigantic, but the previous work shows how this can be generically compressed so long as you locally use the public parameters in the relevant algorithms. So for today, we're just going to assume that it's fine for these to be gigantic. Okay, so what does the secret key look like? Well, we're going to have a non-interactive zero-knowledge proof of the openings to the commitments for I in this set capital I for corresponding to the ID. So where does this come from? So this is going to be derived from some sort of hash function. I'll specify this a bit more later. Basically, this hash function is going to take in the ID and just output the set. And then the ciphertext is just going to be an obfuscated program which checks that the proof verifies with respect to the commitments. And if so, it outputs M. Otherwise, it outputs bot. Okay, so this is the general template. Why should we believe that this would be secure? Well, for one, the zero-knowledge property of the proof should hide the bits of the master key in this identity secret keys. And moreover, the commitment should also be independent of the master key by hiding. And so pretty much everything is independent of the master key except for the actual leakage function that the adversary receives. And so this is where the hash is going to come in. Basically, if the hash is well spread in some sense, then the adversary should not know most of the master key bits corresponding to at least one challenge identity. So more concretely, you can imagine we have 3 identities, and the hash function outputs a set of size 3, and we have a key of 8 bits, and the adversary gets to leak 4 of them. Basically, the idea is that no matter which 4 are chosen, there's always going to be one identity where 2/3 of the bits are not leaked. In this case, it's the second one. And in this way, we can sort of guarantee that one of the identities in the challenge set has some amount of entropy. And using this, we can sort of infer that basically an adversary should not be able to come up with a satisfying proof, which can let it learn anything about the message. And so obfuscation security should hopefully help us out here. Okay, so that's the general template. How are we actually going to instantiate this from I/O? Well, we're going to make one main change, and that's to add an additional IBE ciphertext for a plain IBE scheme, which just encrypts the relevant bits that are being checked in the proof anyway. And the NISIC is basically going to be that sort of both of these are consistent. Like you basically open up the ciphertext in addition to opening up the commitments. Okay, And then correspondingly, the ciphertext is just going to check this new relation. All right, so this is basically the full construction. So how do we actually prove security here? So we're going to use this notion of a dual system proof, or we're going to introduce these semi-functional versions of both the ciphertext and the queried keys. And we want the property that each semi-functional component is indistinguishable from the honest one, and in particular satisfies sort of correctness if you only switch one thing to semi-functional. And then furthermore, we want that when both components are semi-functional, the adversary should somehow always lose in the security game. All right, so from this point on, I'm not going to go over the full proof, but basically just what are the semi-functional components here. So basically, the semi-functional ciphertext is going to be the same as the original, except there's going to be an additional kind of like sort of pointless check here, where we just open up the decryption and sort of check that it's equal to the bits of the master key. And we're going to do this a bit indirectly by feeding it through universal hash and a PRG. This is basically kind of a standard I/O sparsification trick. And the goal is going to be to change the string t to uniform by the end of the proof and sort of make this extra check always fail. So to help in doing that, let's define the semi-functional keys. So the semi-functional keys are just going to be the same as the original, except they no longer depend on the bits of the master key. In particular, we encrypt to 0 with the IBE scheme, and the NISIC zero knowledge makes the proof sort of independent of the master key. So when both components are semi-functional, what's going to happen is that the commitments are again going to be independent of the master key, and we're going to again be in this sort of spot where everything is independent except for the leakage. But as we know from before, this hash function, which chooses the set capital I, is going to guarantee that one of these identities has high entropy. But if it has high entropy, then we can use the leftover hash lemma to make this input to the PRG uniform. And then PRG security basically says that the string t is uniform. And if the string t is uniform, then with very high probability, it's going to be outside the PRG image. And essentially, we can switch by I/O security this program to the null program. And that more or less would complete the proof. So yeah, that's basically the proof for the I/O scheme. Lastly, I'll say a word about extending to witness encryption. The main difference here is that we cannot switch the program logic as we did for I/O for the semi-functional ciphertext. And so what we're going to do is make the semi-functional keys try and do kind of like all of the work in the proof, where the honest ciphertext is going to be more or less semi-functional already. And to help do this, we use basically a type of encoding that could be constructed from standard pairing-based assumptions to help out here. Basically, the encodings do a lot of these like extra checks that set up a similar style of proof. And with that, I'll conclude with some open problems. One thing that would be nice is to prove adaptive security from weaker assumptions like pairings or LWE. Additionally, improving efficiency, sort of along the same lines. And lastly, it'd be also cool to allow the big key to encode like useful information via maybe like a incompressible encoding or something similar, so that it's not just sitting there with taking up all the space and it's just a bunch of random bits. And with that, yeah, I'll take any questions.
So, any questions? Yeah, I guess since you use such heavyweight tools, you anticipate this question. So, what's the difficulty of using less heavyweight tools?
Yeah, basically it's like, basically it's kind of comes down to the security definition is like very complicated and delicate, and sort of even the construction, the selectively secure one from pairings, it's essentially using a special witness encryption for a specific language, and the point is that you can't extend that very easily to the adaptive setting. I guess that's sort of like one reason why the pairing one seems pretty difficult. But yeah, it's a pretty complicated definition to deal with. Yeah.
Thank you. Any other questions? Yes.
Is there a simple way to get adaptive security in the random oracle model?
I think we thought about this, but we didn't necessarily come up with anything for that. Yeah, it's not. I think that's pretty open. Yeah, the hash we use is not actually a random oracle. The one that chooses the sets. This can actually be done information theoretically, but yeah, I guess it's possible that the random oracle could help out. But yeah, I'm not sure.
More questions?
What about the attribute-based encryption? Because you're using dual system proofs, can these results be ported to attribute-based encryption?
Right. So with attribute-based encryption, kind of the problem is that the keys can decrypt potentially many things. And so it's very hard to even define. Like, I don't think we came up with a definition that made sense, because if you have some function that's very powerful, then, and you can sort of decrypt multiple things with it, it's like, I don't know, it's kind of unclear if you're getting any meaningful security out of it. I guess I think that was our main issue with it, but we did think about this a bit.
So if there are no more questions, I guess let's thank Jeff again. Okay, the next talk will be on non-committing identity-based encryption, constructions, and applications. And the speaker will be Mahesh Rajashree, who is a postdoc from CISPA.
Hello. Hello. Okay. Oh, great. Thank you for the introduction, Russell. I'm Mahesh. I'm a postdoc from CISPA, and I'm here to present our paper on non-committing identity-based encryption, construction and applications. So this is with a bunch of collaborators around the world, Rishabh Goyal from University of Wisconsin, Venkatakoppula from IIT Delhi, Fuyuki Ryo and Takashi from NTT Japan. So before going into non-committing identity-based encryption, which I'll call as NCIBE, I'll start with an application, which is incompressible cryptography, somewhat related to big key cryptography introduced by Jeffrey. So since we are in PKC, I believe everyone knows the standard security notion for a public key encryption scheme, which was kind of defined by Goldwas and McLean. So the setup is pretty simple. You have an adversary and a challenger. The challenger generates the public key and the secret key and sends the public key to the adversary. Now the adversary will analyze the public key and give two messages of its choice, M0, M1. Now what the challenger does is, it'll randomly pick one of these messages, encrypts it, and sends the ciphertext to the adversary. Now the adversary will just analyze all these data and just make a guess whether the ciphertext was an encryption of M0 or M1. So it sends the bit B dash as its guess. Now we say the adversary wins if B is equal to B dash. And the scheme is secure if no efficient adversary can win this game with probability more than half plus negligible. Everything's standard over here. Important point is the adversary does not learn anything about the secret key over here. You can define versions where it learns some bits of the secret key known as leakage resilience and blah, blah, blah. So what if in the future the adversary learns the entire secret key? So note that if the adversary learns the entire secret key and the entire ciphertext, then there's no guarantee, right? Because the adversary can just decrypt the ciphertext, learn the underlying message, everything is done. So this is where incompressible cryptography comes into play. It was introduced by Zaimbowski, and later it was extended to public key setting by Juan. And over here, we assume that the adversary gets the entire secret key, but just a part of the ciphertext. Entire secret key and part of the ciphertext, which is different from the big key cryptography where the key is made very large, and you can get part of because of the key is very large, you'll get only a part of the secret key. So essentially, how do you achieve this is you make the ciphertext very large. Instead of making the secret key very large, make the ciphertext very large. It's very hard to store the entire ciphertext for a very long time. So the security game is like the adversary gets the ciphertext, it compresses the ciphertext, and then later it's given the secret key. Now, how do you formally define this? It's again by a game, but now you have a two-stage game. So the first stage, it's kind of similar like the standard security notion, where challenger generates public key, secret key, sends the public key to the adversary. Adversary sends back two messages, M0, M1, gets a ciphertext of the random message. Now, it does not send back the bit. What it does is, it will compress its state. So its state will contain the public key, both the messages, the ciphertext, and maybe some other information also. So it compress the ciphertext to a state, and it should be less than some bound s. In our case, this s is going to be less than strictly less than the size of the ciphertext. Okay, so you should think about this as the phase where the adversary is trying to compress the ciphertext. Forget about the remaining entities. So this is the end of the first phase. Clear? The second phase, this second adversary is given the public key. Notice the entire secret key and the state. So again, what is the state? It's the compressed version of the ciphertext. And now it needs to decide whether the ciphertext in the first stage was an encryption of M0 or M1. Make sense? So let's stare at this for a moment. First thing, if a scheme is secure in the scheme, obviously it's secure in the standard notion, right? Because the adversary one can just send its guess bit in the state, that's it, done. Interestingly, none of the adversary learns this, or none of the two adversaries sees both the entire ciphertext and entire secret key at the same time. The first adversary sees the entire ciphertext, but not the entire secret key, or nothing, no information about the secret key. Whereas the second adversary sees the entire secret key and some part of the ciphertext. Okay? So, as I mentioned, it was introduced, and construction for the first incompressible SKA scheme was given by Zymboski. Later, Juan et al. Extended to PKE, incompressible PKE, and they gave two constructions. One using regular PKE, but it had poor rate. Rate means the size of the message divided by size of the ciphertext. Then they gave a construction from indistinguishable obfuscation with rate 1, a very heavy tool. Branco et al. Gave a construction for CCA secure incompressible PKE from standard assumption and rate 1. Later, Juan et al. Extended this notion to multi-user setting. Bhushan et al. Merged incompressibility and leakage resilience. So the first adversary will get some information about the secret key. Not the entire secret key, but some information about the secret key. Then Goyal et al. Extended the notion to functional encryption scheme, attribute-based encryption scheme, and identity-based encryption scheme. So hopefully by now, everyone knows what an identity-based encryption scheme is, thanks to Vidan and Jeffrey. So what does this have to do with NC? So NC is something like a public key encryption scheme with a bit more security, more powerful than a public key encryption scheme. So if you have an NC and an incompressible SKA scheme, you get an incompressible PKE scheme. This is by hybrid encryption. I'll talk about what is hybrid encryption. And incompressible SKA can be built from one-way functions, the most minimal assumption. So essentially, it's saying that if you have NC, for free, you get incompressible PKE. Make sense? Okay, so what is a non-committing encryption scheme? As I said, it's like a public key, it is a public key encryption scheme, but with a different security notion, where you have an adversary and a challenger. So Eve is going to generate a public key and secret key. And this, so essentially what's going to happen is they're going to play the game either in the real world or in a simulated world. And the adversary needs to distinguish in which world they're living in. So the real world, challenger sends public key, adversary sends a message. And now what the challenger does is just simply encrypts the message under the public key, sends the ciphertext and the secret key to the adversary. Now the adversary will just check for consistency. Maybe it can do like decrypt the ciphertext and get the message back and everything. Okay? So essentially, what is the ciphertext doing? It's kind of somehow committed to the message, right? Because you have to get back the same message back due to correctness. So this is the committing world of the real world. In the simulation world, or which I call the non-committing world, the challenger starts with a public key, but a ciphertext. So it has generated a ciphertext before seeing the message. Now it sends the public key, gets back the message. Now, as the ciphertext is not committed to the message because it does not know the message in the beginning, right? So it's going to cheat and it's going to create a fake secret key, and now going to send the secret key along with the ciphertext. And it should be the case that using this fake secret key, when it decrypts the ciphertext, you see back the message M. So essentially, the ciphertext is non-committing to anything. Later, the adversary can play around and give a fake secret. So not adversary. The challenger can play around and give a secret key, which will decrypt CT to the message. Hence the name non-committing encryption. Now, this was initially used to prove adaptive security in MPC, multi-party computation, and then used in building certified deletion. This is something in the quantum crypto world. And then, as I mentioned, it's used in incompressible cryptography also. Cool. So what is the syntax? How does NC look like? As I mentioned, it's just a public key encryption scheme. So there's a setup, which generates the public key and the secret key. There's an encryption algorithm, which takes the public key and the message and gives a ciphertext. Then there's a decryption algorithm, which takes the secret key and the ciphertext and gives back a message or bot. So this is the algorithm for the real world or the committing world. In the non-committing world, you have a simulator, one, which will generate a fake public key and a fake ciphertext. And there's a simulator two, which when it sees the message, it generates a fake secret key. And the simulator 2 also gets some additional information from simulator 1, but I'm just not writing those information. And essentially what you're trying to say is, okay, the real world entities are indistinguishable from the simulated world entities. Cool. Now, again, I'll just quickly go over what an identity-based encryption scheme is. So it's just a generalization of a public key encryption scheme, where you don't have like 2 parties, you have like n number of parties in the system. And you don't want to maintain 2 and many secret keys, and 2 and many keys, or n many public key secret key pairs. So you have n many secret keys, but just a single public key, which I'll call the master public key. So while encrypting a message, you take the master public key, the person's identity, and just encrypt it. And the security is, the adversary gets a ciphertext, which is an encryption of M0 or M1, under some identity ID star, which is chosen by the adversary, and it shouldn't be able to distinguish the ciphertext, provided it also sees multiple secret keys for identities which is not equal to the challenge identity. Good. So what is the syntax of IBE? So IBE is like you have a setup which generates the master public key and the master secret key. Encryption takes the master public key, identity, and the message, and outputs the ciphertext. Now, since there are like many parties in the system, there should be a key generation algorithm. The key generation algorithm takes the master secret key and the identity of the entity and generates the secret key for that person. And decryption says that, okay, if you have the secret key for ID and a ciphertext which is encrypted under ID, gets back the same message. So this is like an advanced functionality of PKE. Now, as I said, PKE, there's NCE. Similarly, I can also define a non-committing version over here, where the first simulator generates a fake master public key and a fake ciphertext. You have a second simulator which generates fake secret keys. Again, recall that the first simulator does not generate any master secret key. So, whereas the key generation algorithm needs a master secret key to generate secret keys. So somehow it should create fake secret keys. Third simulator will see the ID star and the message and then generates a fake master secret key. Make sense? Okay, so prior works in non-committing encryption scheme, it was introduced by Kennedy et al. In the multi-party setting. And then there have been lots of work improving the rate, assumptions, etc. And there were 2 works which constructed rate 1 NCEs. And all these work, there's a star over there because they deal with this setting where the adversary not only gets the secret key, but also the randomness used to generate the secret key, public key pairs, and the encryption, and the randomness used to generate the ciphertext. So NC is actually a pretty strong entity. But in this talk, we'll be talking about the adversary not getting the randomness, just the master secret key or just the secret key. So Hiroka et al. Introduced non-committing identity-based encryption to build the certified deletion thing. So what is this security notion for non-committing IB? So the real world, challenger generates the master public key, master secret key, sends the master public key to the adversary. Now adversary should be able to get many secret keys of its choice. So it sends identities and gets back SK IDs. In the challenge phase, it'll send a message and an ID star, gets an encryption of the message under ID star, sends the ciphertext and the master secret key, and it needs to guess whether it's in the real world. And of course, it should not query for ID star secret key, or else then there's no point. Now in the simulated world, simulator generates the master public key and the ciphertext. The remaining things is almost the same, except for the simulator will generate the fake master secret key. Okay, and the important point about IB is it's the non-triviality come from the fact that you have n parties in the system, and these n parties can be exponential also, whereas your master public key, master secret key is kind of small, poly lambda. So it's all about compression, and it's pretty difficult and non-trivial to do it. So what question we are trying to solve over here is, can we build non-committing IBE from standard assumptions, standard or weaker assumptions than the assumptions used by Hiroka et al.? They used indistinguishable obfuscation. So pretty heavy hammer. So we want to bring it down to something like bilinear maps or LWE, and that's what we did. So we get rate 1 non-committing IBE from bilinear pairs. And this implies that I can get rate 1 strong incompressible IBE from bilinear pairings and LWE, again by the hybrid encryption methodology. So this was an open problem from the Goal et al.'s paper, whether we can build strong incompressible IBE from standard assumptions. In fact, they didn't even give a construction from IO also, but yeah. We also give non-committing IBE constructions from DDH and LWE, but over here, the number of users is bounded to be polynomial, which is not essentially IBE, but something better than nothing. So I'll just quickly go over the construction. So we use bilinear pairings. So it's just what? You have a function E that maps an element from G1 and an element from G2, which are groups, to an element to the target group GT. And I'll just use G1, G2 to be generators of capital G1, capital G2. And the point is E of G1, G2 should also be a generator of GT. And what is bilinear over here? It says that E of G1 raised to A, comma G2 raised to B is equal to E of G1, G2 raised to AB. So somehow the exponents just jump out of the bracket. It's a pretty cool tool. I'll use this bracket notations to denote shorthand notations of G, B raised to A. So the construction is very similar to the IB construction from pairings, where you have a bunch of vectors and group elements from G1, G2, and everything. For the time being, just see that there's a vector with vectors with respect to A and vectors with respect to B. The setup is the master secret key is just a 2-dimensional vector. That's it. And the master public key is just a dot product of that vector with K in the target group element. The key generation algorithm just uses the vectors related to B in the public parameter and also K. And for encryption, they use the vector from A and then encrypt it. I don't expect anyone to understand anything over here, but for people who know the construction, it's very similar to the construction from bilinear pairings. Sorry. Now, for those who are interested in knowing how is the non-committing being done, the master public is random point in the target vector, target group space. And the ciphertext is a random looking vector, that's it. To generate fake secret keys, it just uses that K1 value. And K2 is no K2, so K1 and K2 will be used to generate the master secret key. So in the simulation mode, you will evaluate or you calculate K2 appropriately and then set your master secret key to this form. Just trust me, it works. So there'll be a lot of hybrid arguments to change your ciphertext to a truly random vector like that. And yeah, with that, I'm not talking more about it. So now how do you get incompressible IBE from non-committing IBE? Hybrid encryption. So I'm going to start, I have 2 more minutes. I'll start with a non-committing IBE and an incompressible S key to get a incompressible IBE. I have not defined what an incompressible IBE is, but it's the same thing. The adversary should not be able to compress the entire ciphertext, and then later, getting the entire master secret key should not be able to distinguish the ciphertext. So here the master public key is nothing but the master public key of the NCIB, and same thing, the master secret key is the NCIB's master secret key. Key generation is just run the key generation of the NCIBs. Now encrypting a message under the identity ID is, you first take your incompressible S key, encrypt your message, so you have to generate the incompressible secret key also. So you do that, and then you encrypt this incompressible secret key under the NCIBE. So essentially, you're getting incompressibility from the first part. in a very high level. And with this, so this is called hybrid encryption. So with this, I'm going to conclude my talk. So question is whether we can get NCIB from LWE or other assumptions. So as I mentioned, our work just does not handle randomness. So maybe whether we can get full NC from standard assumption, even from IO also would be a good work. Then rate 1 NC AB from bilinear pairs. This is being done by us, so no hopes for that. And then whether you can build strong incompressible IB or AB from any other, techniques or ways, not going via NC, IB, or yeah. So with this, I conclude my talk. Thank you. I'll be happy to take questions.
So, any questions?
You should use the microphone for the video.
Hi.
Hi.
Can you give an intuition of where one wants to use incompressible cryptography? Because what I understand is we have very huge ciphertexts,
Right.
and I still have to send them, but they need to be so big that the adversary cannot store them.
So yeah, think about long-term storage, where you want to just encrypt your data and store it. Like imagine government-sensitive documents. So you want to store it over there, no one should touch it, and no one should leak it in the future, but you just expand your ciphertext and keep it over there. So even if they get the entire secret key, they won't be able to get the entire ciphertext out. So that's one application.
Hi.
Hi.
Wait, so for the fourth one, you said strong incompressible IB. I assume that means you give out the master key.
Yes.
Is it significantly easier if you get like unbounded key gen?
No, you have a
instead
separation.
Oh, we have a
Oh, so
separate-
yeah, I don't know whether it's. I feel it's more simpler. We do have constructions for that.
Okay.
Yeah.
I see. Thanks.
Hi. So there's an impossibility result for non-committing encryption in
Yes.
the non-programmable random oracle model. Why
By,
does this not apply here?
So again, over there it says that you can't commit to unbounded many messages, right? Here I'm just talking about one message. That's it.
One, yes. Okay. So
And
one
over the-
message of bounded length as
Bounded
well.
length, yes.
Right. Okay, that makes sense. Thank you.
Thank you.
Thank you. I noticed you had a GitHub link on the end. Is the bilinear pairing construction potentially practical? Oh, okay, that's just your website.
My
Okay,
website.
never mind. But is it potentially practical, implementable?
I didn't check that. just theoretical.
All right, thank you.
Thank you.
Okay, do we have more questions? We do have time for more questions. I'm sorry.
No problem.
If not, then let's thank Mahesh again.
Thank you. Thank you.
Okay, so the final talk in this session will be registration-based encryption in the plain model. And the speaker will be Wei Qi from CIFRA, which is apparently a new organization at Bocconi University. Yeah, please.
Okay, thank you for the introduction. My name is Wei. I'm here to present the paper Registration-Based Encryption in the Plain Model. This is a joint work with Jesco and Julio. So our story begins with identity-based encryption, which has been very thoroughly discussed in the previous 3 talks. Let's do yet another recap. So in IBE, there is a central authority who has 2 values. First, a master secret key, and secondly, a master public key. Now suppose the user Bob wants to send an encrypted message to Alice. What will he do? Well, he will get the master public key. He will use the master public key together with Alice's name to encrypt the message and send it to Alice. Now, if Alice wants to decrypt the message, she sends her identity to the central authority, who will then use the master secret key to generate a decryption key. And then Alice will be able to use a decryption key to get the message. The advantage of identity-based encryption is very obvious. Instead of n public keys for n users, Bob only requires one public key, no matter how many people he wants to talk to. However, there are also issues about identity-based encryption. One of them is that we are putting way too much trust on the central authority. The scheme behaves really well if the central authority is honest, but what if the central authority is bad? When this happens, since the central authority has the master secret key, it can generate whatever decryption key it wants and thus be able to decrypt whatever message it wants. And since the introduction of identity-based encryption, various approaches have been proposed to address this issue. And among the proposed solution, one idea was to let each user generate her own decryption key, and the resultant scheme is known as registration-based encryption, which was proposed in 2018. In registration-based encryption, the central authority who has a master secret key is replaced by a transparent key curator. Here, by transparent, I meant that the key curator has no secret state. And then how does this scheme work? Well, as said before, each user will generate her own public key and secret key. She will send her public key together with her identity to the key curator, who will register the identity and public key to get a public parameter. This public parameter will function in a similar way as master public key in the identity-based encryption. Now, suppose another user wants to join the system. She will do exactly the same thing, generating her public key and secret key, and sending the identity together with the public key to key curator, who will then update the public parameter 1 to public parameter 2. Now, suppose another user wants to join, the exact same thing will happen. I like to make a remark that in RBE, we require the length of the public parameter to scale polylogarithmically with the number of registered users. Now, suppose Bob wants to send an encrypted message to the third user. What will he do? He will do similarly as what he would do in the IBE scheme. He will get the public parameter 3, or in general, any public parameter generated after the registration of the third user, and then use the public parameter together with the identity of the third user to encrypt the message. And then the third user will be able to decrypt using her own secret key. Note that there is actually a price we have to pay for this compactness of public parameter. That is, as more and more users join the system, it could happen that even when you're using the correct secret key to decrypt the message, your decryption could still fail and output a message saying get update. And when this happens, you should ask for the key curator on a decryption update, with which you can then decrypt together with the secret key. Note that this update can be computed from all public information, so all IDs and public keys, and not depending on any secret state. And note that in RBE, it is required that the number of updates for any user is at most polylogarithmic in the number of registered users. Now, since the introduction of RBE in 2018, various follow-up works have studied various aspects of RBE, including making it more efficient or basing it on standard assumptions. However, there is one question that is still left unanswered for RBE, that is whether a trusted setup is required. I would like to emphasize that in all knowing constructions, such trusted setup is indeed necessary. So in this paper, we'll try to answer this question. And our results are the following. We first show that in standard RBE, it is impossible to build it in a plain model. And then we show how we can modify the security definition of RBE to allow for a plain model construction. Okay, so in order to see the impossibility result, let me first do a quick recap of the security definition. So it is a GAN-based definition between an adversary and a challenger. So at the beginning of the GAN, the adversary can register users. The users can either be corrupted, which means that both the identity and the key are chosen by the adversary, or the user can be honest, which means that only the identity is chosen by the adversary, while the key of the honest user is honestly sampled by the challenger. I would like to emphasize that in the standard definition, this registration of an honest user is optional. Now, after the registrations have been performed, the adversary asks the challenger for an encryption of a random bit to either the honest user or an unregistered user. And then adversary wins if it can output the correct bit. I'd like to emphasize again that security must hold even when every registered user is corrupted. Okay, so now we can exploit this property to get an attack for standard RB in the plain model. The main observation is the following. The public parameter is length shrinking of in ID and public key pairs, where CRS is the key for the hash. And then our idea is to simply adapt the non-uniform attack for keyless collision-resistant hash function. Now let's see what the advice for the non-uniform attack look like. So first you need a list of n public key and secret key pairs, and you need 2 lists of n identities satisfying the following properties. First of all, you require there exist an IDJ prime that belongs to the second list but not in the first list. Looking ahead, this will be the unregistered identity that will attack in the attack. Secondly, we require them to be a collision, which means that registering ID1, PK1 till IDN, PKN, and registering ID1 prime, PK1 till IDN prime, PKN will give us the same public parameter n. Now the attack is simple. You basically register one list of identities with the keys, and then you ask for encryption to IDJ prime, and by the completeness of RB scheme, you should be able to use the secret key to decrypt. And this attack is valid since attacking unregistered users without an honest user is legitimate. And so we fix this hole in our new definition, which basically says that the registration of an honest user is now necessary, and adversary wins if it outputs the correct bit and there is an honest user. Okay, so now let's move on to the construction of our work. The main idea is the following. So at the beginning of the system, the key curator starts with a fixed dummy CRS. And then when each user generates keys, she also samples randomness that can be used to refresh the CRS. And then she will send she will send the public key, the ID, and the randomness to the key curator. And when key curator performs registration, it first re-randomizes the CRS using the given randomness, and then performs registrations. And the security of our construction holds thanks to the existence of an honest user. Note that this is a simplified description of our real construction. For example, in the real construction, the honest user cannot just send the randomness in the plane, because leaking randomness could hurt security, and in fact, it does hurt security. So for the real construction, we need more ideas, and please read the paper for the more ideas. For this talk, let's just assume that the adversary cannot see the randomness sent by the honest user. Okay, so like previous works on RBE, our work also follows the general Merkle tree-based paradigm. Let me give an example of the paradigm using the registration of the first user. So after the key curator received the identity and the public key of the first user, it first read from the CRS a key for a hash function, and then basically use the key for hash function to build a Merkle tree, and then publishing the root of the tree as a public parameter. And then encryption is simply an obfuscated version, or like an encrypted version of the following program, which takes as input a public key prime, and using the root of the Merkle tree together with the ID and the key of the hash function to check if this is the one stored in the Merkle tree. And if the verification passes, outputs encryption using the provided public key prime. And then a user should be able to decrypt using the corresponding secret key. The key observation is that if CRS contains only the hash key, then all we need is re-randomizable key for the hash function. And more specifically, we will follow the framework in the paper, registration-based encryption from standard assumptions, which says that RBE can be constructed from PKE, hash encryption, and garbled circuit. And note that the CRS of this scheme indeed only contains the key for the hash encryption scheme, so it suffices to build hash encryption with re-randomizable key. And we observe again that the CDH chameleon encryption in identity-based encryption in the paper, identity-based encryption from Diffie-Hellman assumption, when interpreted as a hash encryption, indeed has re-randomizable key. And how does the key look like? Well, first of all, we work in a cyclic group of prime order P, where G is a generator of the group. And the key simply consists of the generator G together with the 2-by-n matrices, where each element of the matrix is uniformly sampled from the non-identity element of the group. And then in order to re-randomize the key, you first uniformly sample 2 in values from ZP star, and then you raise each element of the matrix to the sampled power. And then it is easy to observe that the re-randomized keys are identically distributed as freshly sampled keys, and that it is hard to invert the re-randomization, by which I mean that given key and key prime, it is hard to find a randomness R that will re-randomize key to key prime. So how does the hash works? Well, it's very simple. So in order to compute the hash of a value x, you first interpret it as a binary string of length n, where xi is a bit at the i's location of the value, and the hash is simply the product of the corresponding group elements. And then similarly, this is how you compute with the re-randomized key prime. And then it is easy to show that by hardness of this discrete logarithm, hash key prime is collision resistant for honestly sampled key. Okay, so I will end my talk with a discussion of open problems. First of all, a drawback of our scheme is that our scheme actually requires linearly many decryption updates. However, we also show that this is necessary under assumptions satisfied by all-knowing constructions on RBE. Secondly, our real construction will require strong cryptographic tools such as I/O, while standard RBE can be constructed from CDH. And as a result of that, our scheme, it will be interesting to see if one can build schemes with better concrete efficiency. Okay, so this is my talk. Thank you.
Okay, so we have 10 minutes for questions until we have to
Fast. Okay.
Hi, about the impossibility result, what was the impossibility result with respect to CRHF? Keyless CRHF is impossible.
Sorry?
The impossibility result, which you were saying, you're basing it on or it's like similar to the
similar to the attack.
So you're saying the master public key is nothing but a keyless CRHF on the...
Yes, you can, well, first of all, the public parameter is length shrinking, and then it's computed using the CRS. So you can view the CRS as the key for this hash function, right? And then you basically just mimic the non-uniform attack for keyless collision-resistant hash function.
Yeah, that's what my confusion is. So CR is acting like the key, but you're using keyless CRHF property or the impossibility result?
Yes, so the CRS as the key, but we are showing that standard RBE cannot be constructed without the CRS, right? So we're saying, like, suppose there is no CRS, then we can use this attack. Okay.
Is it obvious to see that this attack is efficient?
Well, it's a non-uniform attack, so you need to get this advice. Then with this device, yes, it is sufficient. So,
okay, I see. It's like, I see. So you spend unbounded time to
Yes.
get this. I see.
Also, I want to ask here, so the impossibility result only rules out non-uniform adversaries. Can you say something about when you want security only against uniform adversaries? Is that possible in the plane model?
I don't think so. No, I don't know, but I'm more inclined to believe there isn't. No, I don't think so.
Okay, and what about the uniform random string model? So where you have a CRS, but it's just uniform random bits. Are there constructions in that model?
Yes, there are constructions with this transparent CRS where the CRS are sampled honestly, but in this model we're really trying to ask the question of whether RB can be constructed without a trusted setup.
Okay, thanks.
Yeah.
Do we have more questions? So there is this lattice-based RBE with the transparent setup, as you said.
Yeah.
So if I really want to get rid of the
trusted
URS,
yeah.
So have you tried using your techniques to like update the CRS?
For that one,
like what's the difficulty?
No, we didn't do that one.
I see. Okay.
But I think it's yeah.
So if there are no more questions, then let's thank the speaker again.
Okay, thank you.